Today, we are diving into a fascinating aspect of computer architecture, the input-output units. Think of them as the essential gatekeepers that allow a computer to connect with the outside world. Whether it's interacting with a user, communicating with other systems, or managing peripheral devices. Without these units, our computers would be isolated islands with no way to reach out and exchange information. Let's kick things off by talking about where our data lives. Imagine your computer as a short-term memory powerhouse. It uses volatile memory or RAM to keep things running while you work. But there's one problem. RAM is like a whiteboard. The moment the power goes out, everything written on it vanishes. This is why we need non-volatile storage like hard drives, SSDs, or even magnetic tapes. These devices act like journals, keeping our data safe and sound even when our computer takes a nap. Now, if we compare a computer's memory unit to its I/O and storage systems, we find something interesting. Memory is neat, predictable, and structured, like a library with all the books organized and ready to be read. But what about I/O systems? They are much more like a bustling marketplace. Different vendors bring their own unique goods, each with distinct designs and communication protocols. This diversity makes I/O hardware a bit of beautiful mess, challenging, but incredibly versatile. To make sense of this complexity, there are two core concepts we need to understand. First one, I/O access methods, and second one, I/O controllers. I/O access methods decide how data moves between the processor and the peripheral devices. Imagine these methods as different kinds of delivery services. Some might be direct and fast, while others might take the scenic route. Then there are I/O controllers, which act like translators. They take commands from the CPU and convert them into a language that the various I/O devices can understand, ensuring everything works together smoothly. But that's just scratching the surface. Let's zoom in a bit more on the types of I/O units and devices. Broadly, we categorize I/O devices into two groups. First one, human-readable devices. These are the ones we use every day: keyboards, screens, printers, etc. They are designed for us, the users. Second one, machine-readable devices. These are for the computer itself, like hard drives, CDs, and magnetic tapes, which store and retrieve data. When it comes to storage, there's another layer of categorization specifically for mass storage devices. First one, direct access storage devices, and second one, sequential access storage devices. Let's unpack these a little. Direct access storage devices are like a choose your own adventure story. They allow direct access to data using unique addresses. But, and here's the catch, how fast you get to that data can vary. It depends on where the data is physically located and the current state of the device. For example, hard drives, CDs, and DVDs are all direct access storage devices. Imagine the disk as having a series of tracks and sectors, with a read bar write head that moves over these tracks to find what you need. The time it takes to get there consists of three main parts. First one, seek time. It's how long it takes to move the head over the correct track. Second one, latency. The wait for the desired sector to spin into position. Third one, transfer time. How long it takes to actually read or write the data. Sequential access storage devices, on the other hand, are more like an old-fashioned cassette tape. There is no jumping straight to the song you want. You have got to hit fast forward or rewind until you get there. Tape drives work just like this, requiring sequential searching through data. They are slower, but they are still useful, especially for things like backups, where reading everything in order makes sense. So, if we compare DASDs and SASDs, it's like comparing CDs to cassette tapes. CDs lets you jump directly to the song you want, while cassette tapes require a bit more patience, but both have their uses depending on the situation. Another interesting challenge with I/O devices is speed. Let's face it, I/O operations are slow. Imagine that accessing data from memory takes just 10 nanoseconds. Now, compare that to reading one sector from a disk, which might take 10 milliseconds. That's a million times slower. This massive speed difference is one of the reasons we need I/O controllers. These controllers manage input and output operations to bridge that gap. They are like skilled coordinators, using buffers to store data temporarily and then sending an interrupt signal to the processor when the job is done. It's all about keeping the processor from sitting around twiddling its thumbs while waiting for slower I/O operations. So, as we explore these components, I/O units, DSDs, SASDs, controllers, we start to see how every piece plays a role in making computers not only powerful but also adaptable and user-friendly. Understanding these details help us appreciate the incredible complexity that underlies even the simplest of actions, like saving a document or watching a video.